Ladies and gentlemen, hello. I am very pleased to present our work on mechanical behavior and crack propagation of ABS 3D printed specimens, which is for me a worthy challenge and a great pleasure. In this perspective, I will present the work according to the following plan. I will start with methods and materials and then give an overview of results. Afterwards, I will present our conclusion. 3D printing technologies are widely used for the production of polymer components from prototypes to functional structures with difficult geometries. By using fused deposition modeling (FDM), it can form a 3D printed through the disposition of successive layers of extruded thermoplastic filament. 3D printing can create physical objects from a geometrical representation by successive addition of material. According to ASTM F2792, additive manufacturing technologies can be categorized into 7 different categories, which can be better understood by following flowchart. One of the most common materials used for FDM process is Acrylonitrile Butadiene Styrene (ABS). ABS is a thermoplastic polymer, a material which becomes moldable at a relatively low glass transition temperature and solidifies upon cooling. The first step is to create a 3D model of the specimens, a tensile test, and a sent ones to be printed. This model was designed with computer-aided design (CAD) software. The CAD file is then converted to a standard additive manufacturing, an STL file format. The file is then digitally sliced into layers with Cura 4.6 version program and setting up of the machine as shown in the table. The second stage requires the transfer of the STL file. In the third step, the machine builds the model layer by layer. The layer thickness dictates the final quality and depends on the machine and process. For fused deposition modeling, a layer thickness of 0.254 mm is typical for stereolithography. Printing can result in a quality of 0.05 to 0.1 mm. The size of a model depends on the machine size. During printing, the used material take the form of filaments which are unwound from a coil and fed through an extrusion nozzle. The nozzle melts the filaments and extrudes them onto a build sample. The measurement of displacement deformation using the DIC system requires the preparation of the surface of an analyzed specimen. The samples for tensile testing were produced in accordance with BS-EN ISO 527-2012. The dimensions of the samples are shown in the figures. The goal of the study was to investigate the correlation between layer thickness and mechanical properties of additively manufactured parts using FDM. In order to do so, mechanical tensile tests were performed on samples made of ABS. The tensile testing was carried out using a MTS tensile testing machine with a load cell of 30 kN. The crosshead speed was 10 mm a minute according to the standard. The image at the right represents a tensile test result of a sent printed specimen. Tensile testing on a printed and extruded of the studied material are undertaken. The mechanical behavior of each of the specimens are analyzed. The shown table presents the different properties of a printed and an extruded one. Tensile testing on 4 different infill rate 20%, 40%, 60% and 100% of the study material are undertaken based on specimen geometry as presented in the figure. The mechanical behavior of each of the specimens are analyzed. It can be seen in the trend line that the strength is proportional to the mass of the specimen. A higher level of density resulted in a lower amount of voids in the infill, and, subsequently, high tensile strength were at 20% density. The tensile strength is the lowest, but at 100%, the value is the highest of all of the results. The printed specimen show the highest strength, while the extruded one exhibited the lowest ductility, thus the lowest elongation to break value. We observed that the yield modulus decreased slightly between a printed and an extruded ABS. The figure represents the evolution of crack length in function of time for both samples. At the beginning of the crack spreads linearly and the both samples adopt a same behavior. After 15 seconds, the crack's behavior on the printed specimen diverge. The damage is not localized at the bottom of the crack, and the creation of a new surface is done randomly. The curves present the variation of SIF on mode 1 as a function of crack length. Then we can observe that the SIF for both specimens increases exponentially after exceeding the 7 mm critical defect point, where no judgment can be made because the formulas are not applicable in this zone and the values become unreliable. Before the 7 mm point, the SIF increases uniformly in this zone and is represented by the central regime of the propagation of a crack known as B regime. Beyond this zone, it's the mode C, or the propagation of the crack becomes uncontrollable and exceeds the values of the speed envisaged by the law of Paris, and the critical stress intensity factor is exceeded. KIC. Comparing the two curves, is clear that the printed sample adopts the same behavior as the extruded one. The mechanical properties, the ductility and fracture toughness, are identical, and compared, printed and extruded samples towards crack propagation are comparable. The stress intensity factor is determined. The results indicate a considerable effect of the density and the filing rate on tensile properties and on the rupture propagation.